In Math 2, you learned how to reflect images on the coordinate plane. Remember that a reflection is a rigid motion transformation, meaning that the distance and angle measures within the shape are preserved. In other words, even though the pre-image and post-image are in different positions on the coordinate plane, they are the same shape and size. A reflection moves points across a line of reflection in a very specific way. When you connect a pre-image point with its corresponding post-image point, the line of reflection is the perpendicular bisector of that connecting line segment. Let's look at an example. The point A is reflected across the line y equals x to another point. The line y equals x bisects the line connecting the 2 points, so both points are equidistant from the line of reflection. Here is another example. We see that the triangle ABC is reflected over the line y equals x. How does each pre-image point compare to its corresponding post-image point? What can you generalize about reflections over the line y equals x? Today in class, you worked on the task Reflections of a Bike Lever. In that task, you continued working with absolute value functions and practiced graphing nonlinear absolute value functions on the coordinate plane. You also wrote the equivalent piecewise defined function for each absolute value function. There are 2 key points to remember when you're writing a piecewise defined function for an absolute value function, y equals the absolute value of f of x. The first is the behavior of the interior function f of x determines the domain of each subfunction. Each time the graph of f of x crosses the x-axis, you must create a new subfunction. The second is when the interior function f of x produces negative values. For example, when the graph of f of x is below the x-axis. Create a subfunction that reflects these negative values across the x-axis. You're essentially writing the opposite equation to make these values positive. Consider the following graphs of f of x and g of x. We see that the graph of the interior function f of x crosses the x-axis at only one point, which is when x equals 2. So the piecewise defined function for g of x will only have 2 subfunctions. Additionally, for everything where x is greater than 2, you need a subfunction that reflects all the negative values of f of x across the x-axis. So the piecewise defined function for g of x would look like this. You studied exponential functions in Math 1 and Math 2. We learned that the exponential is the function that models geometric sequences, meaning that you have a common ratio a that you are repeatedly multiplying. When using an equation to represent the function, c is the initial value, or your y-intercept. If the common ratio a is larger than 1, it is a growth model, and if it is less than 1, it is a decay model. A is always 1 plus or minus the percentage of growth or decay. If you are trying to find the equation when you are given a table, look at your y values, the outputs, and find the common ratio. This is A. To find C, you need the y-intercept, or where x is equal to 0. You can work the pattern backwards to find it once you know what the common ratio is. Then you have what you need to write the equation. Let's look at an example of the graph. Graph f of x is equal to 3 to the x. Remember that the exponential graph has an asymptote on the x-axis. Its pivot point is on the y-axis and is c spaces above the asymptote. A tells you whether it is growth or decay.